I think you'll find
Say public class.
Oh.
This is why we didn't have that. Yes.
Okay, guys, I think you're gonna find this whole few days is really easy. You already know how to do all these things. You have to now involve complex numbers, but it's the same exact process. You have to know what represents what. So yes. So today we're just going to add and subtract complex numbers. It's going to feel like a lot of this is going to feel like vectors that you already know how to do. Then we're going to do a practice for the checking quiz tomorrow. So checking quiz is just going to go over a few topics that you see on that separate handout. We'll go over that. And I'd like to go ahead and get started with complex numbers in formal form. Again, you already know how to do this. It's just to be able to know what represents what for complex numbers. Okay, but the process you already know how to do. So a lot of this will just feel like review. So today we're going to finish up a rectangular form, and then we're going to start polar form, and go back and forth between rectangular and polar. Okay. All right. So if you guys can turn to 7.06, this is going to be page 16. Okay, so recall that complex numbers take the form of a plus b I. When adding and subtracting complex numbers algebraically, the real parts get combined together or combined, and then the imaginary parts are combined. All right, so similar to adding like terms. Right? Complex numbers can be added or subtracted geometrically or graphically by plotting the points in the complex plane and creating vectors with them. Then using geometric a vector addition or subtraction. So let's do the easy one first, which is algebraically. So we're just going to add the like terms together. So 5 and 8 combines to be, sorry, 5 and 3 gives us 8. And then the imaginary components, we add those together, we can also get. So now the way you're going to represent this algebraically is you're going to create a vector 5 plus 2i. And then on top of it, you'll build 3 plus 6i, and then you'll go from initial to final, and that should be the 8 plus 8i vector. So we'll start with 5 plus 2i. So start at the origin. We're going to go 5 to the left and 2 up. So, sorry, 5 to the right, and then 2 up. And then we're going to pick up where we left off. 3 plus 6i, so to the right 3 and up 6. 3. And then our resultant vector should be 8 plus 8i. So let's confirm that's the case. So 1, 2, 8. Yes, so this resultant vector matches what we know to be true about algebraically adding them together. So that's really all there is to it, right? You already know how to do this. Okay, so -3 plus 4i. And then really this is 0 minus 10i, same thing as 0. I'm sorry, negative, yeah, 0 minus 10. Combine like terms. Okay, so here's our algebraic resultant, and then let's see if we can get that to show up graphically. Start with -3 plus 4i. Okay, what's 0 minus 10i gonna be looking like? Straight down, yeah. I'm not gonna go left or right, I'm gonna go straight down. Okay, your resultant vector is just from your initial to your final destination. Go ahead and count that. That should match -3 minus 6i. Go left 3, down 6. If we're subtracting algebraically, I think you won't have any trouble. You just have to be careful with the way you make the adjustment geometrically. So here, I can combine like terms. 5 minus 6, that's -1. Negative I minus a -5. That's -1 plus 5, so plus 4i. Now, geometrically, this is what I would suggest. If you're subtracting, you're going to have to change the signs. But maybe you can, before you do geometrically, why don't we make this into an addition between two vectors? That way you don't have to do something opposite from what you're seeing. So this is the same thing as saying 5 minus I plus what? Yeah, -6. That way it feels more straightforward, right? Because you can just graph this vector, and then you can just follow the signs and not have to worry about subtracting and changing it later. Okay, so that's what I would do geometrically here. So 5 minus I. From here, we'll pick up where we left off and we'll go left 6 and up 5. So then our resultant vector is from here to here. So left 1, up 4. So algebraically, geometrically, it should match the same. Try number 4. Again, before you graph it geometrically, turn it into an addition between the two vectors. That way you don't have to do something different than what you see on the paper. Okay. Page 17. Let's just let's do 1, 2, 5, 6, 7. Everybody good with number 4 on page 16? All right, so on page 17, 1, 2, 5, 6, 7, and I'll show the answers, but hopefully you find this easy.
the guy and -10, -7 on the graph, or can we just write final resultant?
You can write the final resultant, but I want to see it algebraically and graphically.
Okay.
Sorry, number 2 kind of went off the graph a little bit. Okay, and again, for 5, 6, 7, try to convert a subtraction into the sum of two vectors, and that way it'll just make it easier when you're putting it onto the graph. Everybody okay with 1 and 2? Okay, next up, we're going to, yeah, I'll leave this on here for another minute or so. But next up, we're going to go to the complex numbers practice. We're going to have a short check-in quiz tomorrow. It'll look like this. We'll just practice through it, make sure you're okay. And then I want us to start the next section so that we can split it up between today and tomorrow. Okay, so let's go to the practice sheet that you guys picked up, up there at the front. Okay, everybody familiar with 5, 6, and 7? Okay, so, the second quiz will basically cover these items here, so I'll go over, these problems one by one. So first is modulus. This is on the back of your calendar, by the way, these formulas. So, absolute value modulus, basically just Pythagorean theorem, defining, the magnitude of your, complex number or your vector. This is between two complex numbers. This is where we first subtract, the two vectors or the two complex numbers, and then we just treat it like how we would, with modulus. We just take that resulting, complex number, and then we find the modulus, find the distance. And then midpoint, we add the like terms together and we divide each by 2. Okay, so number 1, it says plot -3 minus 2i and find its modulus. So just plot it like how you would normal order pair. Modulus just means, distance or magnitude. So go ahead and put it in absolute value bar to indicate what you're about to do. And then the formula is Pythagorean theorem. Imagine you're just finding the hypotenuse. Yeah.
Is the check-in quiz gonna be a quiz grade or is it like, okay, it's just.
It's gonna be short. Okay, number 2, find the distance between 2 points. So here's the formula. It's find z1 minus z2 first. And then once you have that set up, then it's just gonna look like something like number 1. You're just gonna find the modulus after that. Okay, so z1 minus z2, that just means we're going to take the like terms and subtract them. So 1 minus 3 is -2. -4 minus 6, 2. And now just treat it like how you would number 1. You just find the modulus. Okay, number 3, find the midpoint of the segment connecting, the two complex numbers. So here's the formula. Z1 plus Z2 divided by 2. So we're just combining like terms and dividing each by 2. So 4 plus 1. -11 plus 7. Let's split it up into a plus bi, so any questions with those? Oops, I'm sorry, -11 plus 7, my bad. Negative what? Yeah. Negative. Is that what you guys got? Okay. Yeah, so we're adding, right? So when you're finding distance, you're subtracting your complex numbers first. With midpoint, you're just adding them. So 4 plus 1 is 5, negative 11 plus 7 is negative 4, and divide by 2 each part.
During as a point, like if I were to comma -2.
So if we're trying to find the midpoint in complex number form, we always write it in this form, right? Just like how if I had -3 minus 2i, we write it as -3 minus 2i, but we treat it like an ordered pair.
For the 5 minus 4i, is that a 0 or 2?
This is 2. Right, yeah, it should be a 2.
Oh,
And then number 4 and 5 should be familiar, right? We just got through doing those, so you can try those. Any questions about this? Okay, so tomorrow we'll spend like first 5-10 minutes of class, take the check-in quiz, and we do the second half of the lesson. Okay. But I want to split it up so that we're not having to do the full lesson tomorrow. So today we'll do page 18. Tomorrow we'll do the check-in quiz, and then we'll do page 19. Now, the form is going to look different. It's going to look a little strange, but you already know how to do this. Okay, I just want to be reminding you that you already know how to go from rectangular to polar form, from polar form to rectangular form. From rectangular to polar, you just have to involve inverse tangents and Pythagorean theorem. Okay, so you already know how to do this. It's just the form looks a little bit different. All right, page 18. Okay, so polar form of complex numbers, also known as trigonometric form. And we know what polar form looks like, right? Polar form is radius followed by theta. So polar form of complex numbers, you already know what polar form is. We need to find the theta, we need to find the radius, but it's going to look a little different in complex form because there's going to be that I involved. Okay. So, but once you find your R and your theta, you're just going to put it in this form, but you're going to find everything the same way. So here's the polar form of complex numbers. Z equals, so Z represents that we're doing something in complex number form. And then you have to put the R and theta in this form. It looks like this: R parentheses cosine theta plus, sorry, plus not T. this is the way that I want us to be comfortable with for now, but then down the road, there's going to be a shorthand form of this, so you have to write it all out every time. And we're just focusing on these letters here. So it's the R, C, I, S, theta. So putting it all together, it's just R, CIS theta. So rather than having to write it all the way out, R cosine theta plus I sine theta, this is a shorthand form of writing it. But for now, I would like for us to get comfortable with this so that we know what this means. And then once we're really comfortable with this, and then we're down to, doing multiple problems, and you want to write this all the way out, then you can go to the shorthand form. But for now, I want us to know what it means. So let's stick with this form for now. Abbreviated form. So we know the complex form is A plus BI. And then the real components is basically like the X. The imaginary component is like the B. And if I have the radius and or if I have A and B from rectangular form, I can get it into polar form by using Pythagorean theorem and inverse tangent. So this is rectangular form. So if I want to find R and theta, just like from the previous units, we can use Pythagorean theorem and inverse tangent. Okay, let's do a few examples of what this looks like. So graph each complex number on the rectangular plane, then find its polar form. So we're going to find R and theta and just put it into this form. Where theta is between 0 and 2 pi. So everything's going to be in terms of radians here. So let's do this. 0, negative 10i. Where's that going to go? That's just an order pair. Where's that going to end up? Yep, 0 plus 10i. Yep, that's 0, 10, right? Okay, just mark that off as 10. Okay. All right, let's find the radius. So radius is just square root of a squared plus b squared. That's easy, right? That's just equal to what? Square root of 100, which is 10, right? So anytime you're moving along the axis, the radius is the same as what that value, right? You just, if you're counting along a horizontal vertical line, there's really no need to go through Pythagorean theorem, but you can if you wanted to, but you can just count that distance. Now, in terms of theta, where is this pointing at? 90, but in terms of radians is what? Theta is just pi over 2, yeah. You can go through inverse tangent, but it's easy to tell just by looking at this, right? It's 90 degrees or pi over 2. Right. I mean, you're not going to be able to do it algebraically because it doesn't exist, but we know that it's pi over 2. Okay, so now let's put it into polar form. So all we do is we take R and theta and we just put it into this polar form. So instead of R comma theta, we're going to put it into this complex form or this trig form. So R is 10. All right, number 2, 4 minus 4 root 3I, which quadrant this is going to be in? Fourth. Okay, I'm just making a mark here and plotting that point. Over to the right 4 and down 4 root 3. Let's find our radius. Now, this is important here. If you plug this in the calculator, make sure you use parentheses. Otherwise, if you just do 4 root 3 squared, it's not going to quite get you the correct answer, right? So you want to make sure that the exponent knows to square both the 4 and the root 3. So the way to do that is you got to use parentheses. So practice doing that. You got 4 squared plus 4 root 3 quantity squared. Make sure you're able to get that 8 to show up in your calculator. Everybody okay getting that 8? Okay, let's do inverse tangent. Now, I think it's easier to do degrees first and then convert from degrees to radians because your calculator is not going to get you the proper radian as easily. So make sure you're in degree mode. Now, just like before, we got to make the adjustment, right? The calculator is going to give us the reference angle and we have to get it into the correct quadrant. What does the calculator give us? If you're in degree mode. -60, but which quadrant do we know we have to be in? Right, this is what? Fourth quadrant. So how to get that in the fourth quadrant?
Plus 360.
Plus 360. Now to convert from degrees to radians, you're going to involve 180. So this is how you do it. You do 300 degrees. You want degrees to cancel out, so you do pi over 180. Yeah, this is from previous unit. But you can also just rely on unit circle value, right? You know that 300 degrees is that 400, that fourth quadrant 60-degree measure. So if you recognize this as just pi, as 5 pi over 3, then you're welcome to do that. But if you want to just confirm, you can also use this. But oh, and also if you do this in the calculator, just do 300 divided by 180. That pi is going to throw you off. So just get that 300 over 180 will get you to that fractional value that you recognize. Right. Okay. And now let's put it into this form. R cosine and sine. Put this here.
What's happening?
Because in the end, we want theta to be between 0 and 2 pi. Yeah.
So let's straight with radians and we just did the tangent step in with our calculator in radians, we just add 2 pi and answer because that's what
It's hard to recognize it though. Like I feel like if you can recognize it and convert to 5 pi over 3, it's great. But I think it's easier to get the calculator to give you something that feels more familiar and then go back to radians. It's not, yeah, I want exact. Yeah. So I think the best way to get to exact is go through that additional step. Then you won't then you can recognize that decimal. It's harder to recognize that decimal than to do from degrees to radians. Okay, so my radius is 8, so 8 parentheses cosine 5 pi over 3 plus I sine 5 pi over 3.
So it doesn't matter that -4√3 is negative, it's always add when it comes to the final equation.
Yes. And let me point something out here. If you were to distribute this through, okay, cosine 5 pi over 3, sine 5 pi over 3, distribute the 8 through, it will take you back to this 4 minus 4√3i. Because cosine 5 pi over 3 is 1/2. 1/2 times 8 is 4. Sine of 5 pi over 3 will give you -√3. Sorry, -2√3. And then, I'm sorry, negative √3 over 2, and then 8 times -√3 over 2 gives you -4√3. So if you were to distribute through, it should always get back to your rectangular form. So you can always double check that way as well. Okay, let's do 2 more where we're going the other direction, and then we can stop. Okay, it says graph each complex number on the polar plane, then find its rectangular form. So what's our radius? What's our theta? 120. So that's the first thing we learned, right? How to graph this. So which quadrant will this be in? Second quadrant. This is a 60-degree reference angle. So just go out 5 units. This is a +5, so we just go towards the quadrant that they're referencing. If I want to find rectangular form, I can just distribute the 5 through and get it down to a plus bi. So cosine of 120. Use your calculator. It's -1/2. Sine of 120. Positive √3 over 2. So if I want to get this into rectangular form, it'll just be -5/2 plus 5√3 over 2i. But you can also plug the calculator and make sure, as long as you're in proper degree mode, this will get you that answer as well. Now, the graphing calculator may not do this as well, but you should be able to just use your unit circle knowledge to get it down to the exact value, right? Okay, let's try number 4. Go ahead and try number 4, and I'll work alongside you guys. Okay. Where's 7 pi over 6? Which quadrant? Third quadrant. What's -2 going to do to it? Push, that's right. Push it to the first quadrant. sorry, and I distribute -2 through here. Okay, if we need to, we can review unit circle values so that we're able to get to these exact values. If your calculator is not giving it to you. Okay, this is not going to be on check-in quiz tomorrow, but I wanted to just get ahead. And then tomorrow we'll do the check-in quiz and do page 19. Okay, all right, I'll get your phones.
Review or check please.
Okay,
Will you review?
I'll let you guys review for a few minutes.
Okay.
That's all we know. That's nice.
Get your phone, come back, get your phone.